Welcome to the afternoon session, everyone. Thank you for recaffeinating so that we can come and dive back into the world of supermassive black holes. We're going to start off the afternoon discussion session with Chengcheng Shin from Columbia and Daryl Haggard from McGill, and they're going to talk to us about supermassive black hole binary observations.
Okay, awesome. I guess, do I go first? I can't quite remember. I don't think the clicker works, right, without the USB. Now I have to figure out which computer. Okay, here we go. Can I click there? Oh, great. Okay. Hi, everybody. Sorry about that. I'm Daryl Haggard. This is borrowed from our introductory slide deck for the workshop overall. So I study mostly single supermassive black holes and then smaller mass black holes in binary systems. And I use all sorts of messengers and different types of observations. And so we're going to just introduce ourselves very quickly, but Chengcheng is much more important than I am because she actually knows a lot about supermassive black hole binaries. So take it away. The mic. Can she have a mic?
Yeah. I think the reason why I say a few more words is because I'm not as well known as Daryl. Yeah, I've done a few works related to supermassive black hole binary candidates and also semi-analytical model for the population. My advisor is Zoltan. I don't know where he is, but yeah. I guess the source PG1302 has been mentioned a few times today already by both Julie and Xin Liu. It is a candidate identified by Matthew Graham in 2015. So it was among other 115 sources that had optical periodic variability observed by Catalina real-time survey. But someone might argue, as both Xin Liu and Julie mentioned, there could be false positives, such as stochastic variability of quasar or red noise. I'm sure someone in the audience would love to share your words on that, like Alberto. I can't see him. Yeah, so additional features to identify the source if a binary is needed, and one of such feature is the relativistic Doppler boost. And it was first proposed by Dan in the same year. So basically for stellar people or people not familiar with Doppler boost, is if you have optical and UV emissions from the mini disk of the supermassive black holes, those two variability vary in tandem, and that's because the UV and optical emission from the mini disk share the same Doppler shift frequency. If you're interested in theory, Dan maybe can tell us more about it. So as a result, the UV amplitude is boosted from the optical, and the two variability tracks each other. My other two works related to supermassive black hole binary are more belong to the next session on population. So this work with Kira Mingarelli is a semi-direct application to this work where I looked at the 150 optically varying sources from Catalina and evaluated their PTA detection prospects, where we use Hasasiya. It's a code by Jeff Hasbone, and it assesses the detection background by nanograph and also future detections in PTA experiments, as well as SKA. And we found some promising sources for future targeted searches in those experiments. And the top work is with Zoltan. So for this one, we evaluated the number of quasars that we would see in LSST during approximately 5 years of observation. So for this one, we took the quasar luminosity function. It's observational based by Girish Kulkarni from 2019. And we evaluated the double power law luminosity function for each redshift, for the redshift and mass range in LSST. And we concluded, depends on how deep LSST can go, you might get 20 million to 100 million quasars during the time of its operation. And then we evaluated how many of those could evolve into the LISA band. For that, our results was, again, LSST is the main constraint, but we might be able to detect, I think 30 to 150. My memory is a little blurry in LISA under some reasonable assumptions about binary fraction, quasar lifetime, as well as some uncertainties in luminosity function. Yeah. So in this next slides, Daryl and I summarized a few questions that we could discuss. I'm just going to read through these. So after these slides, I think there are 2 slides related to the questions, and we're going to flash through some slides that you contributed, and then we'll go back to these questions and see which one is of interest.
Yeah, let me just stop for 1 second and just tell people the format that we came up with was since people sent us beautiful contributions, but we don't want to have a whole bunch of mini talks, we're going to just click through them very fast. It's like a dance party. And then you will know what we have on hand to feed these questions. So we're going to show them to you quickly, and then we're going to come back to these questions, and then you know what stuff you can draw on in our slide deck as we have our discussion. Okay, go for it.
Yeah, that sounds good. Okay. So first part of the question we came out is there's this problem with mass estimates in a lot of the methods that we know for supermassive black hole binary candidates. And some of these are reverberation mapping, through spectral line and gravitational wave constraints, as well as the galaxy for supermassive galaxies. So in particular, M black hole, M bulge, or M sigma relation that Julie has also mentioned earlier. So there are uncertainty related to all of these methods. I was wondering what people are thinking for these different methods. And also some other parameters might introduce uncertainties such as periods, separation of the binary, and also selection bias, especially important for high redshift candidates. So, and the next one is how comparable are the sensitivity of different gravitational wave instruments in terms of the SNR. I know the standards is very different for different gravitational wave instruments. The last one that we came up with is what we can do with the ENM observations for these supermassive black hole binary candidates. Some of the potential topics for false signals are the following. Oh, sorry. So astrometry, emission line, jets, and line curves for periodicity. So in the next slides, we summarize a table of binaries. I think Daryl started this on Slack.
Yeah. Oh, I've got my mic. Thanks. I have to be careful not to make too many off-color comments since I'm mic'd up. This was something actually that was Zoltan's idea while we were in the workshop this last week, was to just try to get our highest quality candidates. We do not have some of the really exquisite, fully resolved observations that our stellar binary compatriots have shared with us over the last weekday and weeks. But we do have some nice candidates. You can see sort of the top ones we pulled together. There are 11 sources up in the upper right there. And then some of the methods that were actually just borrowed from Julie's talk this morning. These are not intended to be complete. This is actually a spreadsheet that we have just barely started putting together. I'll put a link to the spreadsheet in the Slack for those of you who haven't seen it already. And please contribute to this. We're not actually really sure that we have everything we need here, but and we hope this list will grow. Recall again, this is not intended to be populations. Populations is coming up in our next discussion. And so there we'll talk about larger samples of things that are interesting candidates, but not the sort of individual objects where we can do detailed studies. So this is, again, intended as a resource for us to be able to come back to it on and off as we go through our discussion. Oh, and also I just, Scott Noble at one point mentioned that Sarah Burke's fellow hour might actually have a table like this in the works. Probably many of you have your own samples like this. So if somebody has just a better resource, please just point me to it. I don't need to reinvent the wheel. Savik's already like, I have one. Yeah, no, go ahead. Should we run a mic to you? Do you have a comment? Wait, no, don't talk yet. Here.
Sorry, no, I just have a question. You said this was on Slack, and I'm just wondering where.
Sorry, we have like 8,000 Slack pages. I will post it right after the discussion, or somebody who's on the other Slacks from our discussions last week can just move it on over. It's open and public for anybody who has access. Yeah, let me come over to you, Laura, just a sec. Oh, Kiara's got it, or Caitlin.
Thanks. Yeah, I actually just want to make a PSA to the folks who are here for the program. The people who are here for the conference only have been given the names of the day 1, day 2, day 3, day 4 Slack. So if you want people at the conference to see something on Slack, put in one of those, please.
Yeah. Just keep calling.
Anybody can join. If you just do a add channel and do binary 22, anything that we have created will come up there. So join any binary 22 channel that you so desire. I don't think there's any restrictions on who can join. So you
I
should
mean,
be
to be fair, there have been a few access issues for people that have been at KITP meetings before, like Chengcheng can't access anything.
Okay, yeah.
So if you
They're
have
meant
problems,
to be public. If they're
yes,
not,
if you have
tell
problems,
us.
let us know.
Yeah.
And also please just keep calling out if things seem to be missing or you're not in the channel where you can see it, because that's really easy for us to move it over. We will do that. Was there another question or comment? This is a discussion. Just stop us at will, ad hoc at any moment.
I'm Ian Chikala from Penn State. So it was on your previous slide. So I was wondering what the physical origin may be of the red noise that you've been mentioning.
Okay, hold your thought. We're going to come back to that in just 1 second. Savik, did you have something related to these things? Okay, yeah, because I'm just going to click through these slides and then these questions are coming right back up and we'll start with your question. Yes.
I have a couple of missing mechanisms up there that potentially microlensing of strongly lensed quasars, if any of them were binaries, and you've got, you can get a microlensing light curve where you could see some very close binaries that way. And transits also similarly, right? If you can map the accretion disk and if you can see two ISCOs or something like that, right? Just a couple of, just not that I have any specific examples of those actually finding anything, but there are potential searches that could work on a population basis.
That'd be super cool. We have one flare from Sagittarius A star in the X-ray that's actually double peaked and almost looks like it might be a lensing signature. So
I also have a student who's about to publish a paper on strongly lensed AGN. So
yeah, thank you. That should be here on the list. Yeah, it's a very good point. Okay, so let us do our quick dance party just so you guys know what's in our slide deck. Okay, so we have a nice contribution from Kiara and also Chengcheng. So this is about sort of populations. They'll come back to this. Just keep going. We're going fast. Okay, and then we have some nice contributions from Sebastian Honig. Gravity has been doing amazing things with astrometry and other stuff. So some nice binary candidates from this work. Sebastian, are you on the Zoom? Yes, I see.
Yes.
That. Amazing.
I'm here. It's late, but I'm here.
Wonderful. Keep going. And then, so this was something that I wanted to just throw out there. So Julia mentioned this morning about next generation BLA. This is next generation EHT. So this is stolen from the black hole working group there. So we hope to be able to do some of the really nice, very, very high resolution imaging with that too. So this has another, just keep on moving. And then this was a nice contribution from Stephen Taylor about galaxies in the kind of local universe and thinking about whether or not we can use, again, nanograv to look at what's going on in those systems. This is a related slide from Stephen Taylor, so let's keep moving. And then we have some nice contributions here from Dan. This has animations, so you'll have to go kind of fast. This is the spiky quasar, or spiky candidate that you guys might like to hear more about from Dan or Chengcheng or others. I think there are a couple of slides on this one. So this is some really nice photometric work. And then we have these really cool tidal disruptions, which we didn't even realize were so interesting, that Kimi Hayasaki shared with us just over lunch today. So a couple of really neat looking periodicity studies for dual black holes with tidal disruption events. I think that was it. Okay, so we wanted you to see the suite of amazingness that is in here. Okay, so now these are the same questions. Let's start back with the question about red noise, because I did not mean to stop you. Can you just re-ask your question? And now people know it's in our slide deck, and we're happy to have the people that contributed these things dive in at any moment in this conversation.
Thanks. I'm from the stellar protostar community, so I was wondering if you might be able, or if it's known what the physical origin of this red noise may be. Is it well characterized?
Red noise. Who wants to share something about red noise?
Which red
Scott,
noise?
Go for it.
There's so many
There's
noises.
So many.
I guess the one that mentioned that we don't have cycle.
Yeah.
Just with periodicity.
The damped random walk.
Yeah, please.
So it's been modeled analytically in the past as a train of stimuli accreting with some sort of parallel distribution, and so you get this pileup of multi-scale phenomenon, and you can get kind of red noise phenomenon, but the red noise is actually nu to the -2, but you typically see nu to the -1 power. And if you actually process I got that wrong. I think it's nu to the -1 and m dot, but you get nu to the -2 when you process that in light due to the superposition of all these annuli and how they emit. We have a paper on this from 2009, was it? Yeah, that kind of does this kind of self-consistently with an accretion disk simulation and a radiative model of emission through the corona. Yeah.
Okay, but let's make sure that we only are speaking when we have mics, because people on the Zoom, if you don't have a microphone in front of you, just can't hear you. So
physically, the origin is turbulence fluctuations. There's MHD turbulence in these systems, and that produces a broad spectrum of fluctuations.
okay, but Kiara, will you talk about another source of red noise? So we use red noise to like be a bunch of different types of processes. So that's one. And typically these are in time series where you can have a time series that looks periodic that is actually just red noise. And so until you've seen, I think 4 cycles is typically the number that people like to have seen at least that many cycles in order to really say something is periodic, or to like walk away and not look at it for a while and then come back and be able to recover the same periodicity, because just the red noise processes in some of these accreting systems can masquerade as something periodic. Zoltan, go ahead.
A quick follow-up. I wasn't aware of this prediction from your old paper, but do you actually predict the break? Because the red noise, what you call red noise, what Chengcheng referred to, is very well characterized observationally from measuring quasar luminosity fluctuations. And it's reasonably described by a Gaussian process with a power spectrum that has a very clear break. So it's red, but turns to white at low frequency. So does this model actually predict also the break?
Okay. Wait for the mic. Give it to
No,
Scott.
wait
Give it to
for the
Scott.
mic.
Give it to
Wait
Scott.
for the mic.
Give it to Scott.
Ours predicted the high frequency end. The break occurs at much longer dynamical times than we could simulate.
Okay.
There's a
Yeah, go for it.
Mark Cabrera. This is somewhat related, though maybe a little bit different. I was wondering if people do blind injections in these searches of fake sources to try and have a characterization that can normalize for differences in the ways of treating red noise and that kind of thing in searches.
Is that a response to the? I'm happy to share.
Yeah, so recently a graduate student, Caitlin Witt, being advised by Maria Carisi, did a systematic study of what happens if you try to fake a bunch of binary signals or periodic signals with damped random walk processes, and established these kinds of requirements for getting a robust periodic detection versus, getting lucky with some random cycles. So it usually takes about 5 cycles.
Thank you. Yeah, Dan.
I also think the first part of Ian's question is interesting. At least I wasn't aware that we've perfectly characterized AGN noise. So are there any observers and AGN observers in the room that say something about how well we really understand this noise process? Is it really a damped random walk at all timescales?
Savik has some strong
She
feelings.
does have strong feelings, hand-waving feelings.
No, it's not a damped random walk. The damped random walk does not actually fit the observed variability outside of a certain range of timescales. So once you go shorter or longer, it under or over predicts. I think that's, but yes, damped random walk is a reasonable approximation for a certain range of timescales, but you shouldn't, it's absolutely not the truth.
You guys are making me so happy. We're going to go 1, 2, 3. Make sure you say your name, even if you've said it already.
I'm Steve Taylor. It's not clear to me that the kind of intrinsic variability or red noise variability would be the same in binary systems versus single AGN. And is that wrong thinking? Should it be the same character noise, or do we have to come up with a different model?
Yeah.
Can I just add one point?
Yeah.
To what Steve is asking? To my understanding, there really isn't a difference, if I understand correctly. But sometimes I think there's one paper that says stamp random walk could mimic the periodicity of the optical variability. So sometimes that becomes problematic. There's a question on Zoom.
Just 1 second, Sebastian. Yeah.
Yeah, so just a follow-up comment on that. I think a lot of the damped random walk models for single black holes are at least confirmed to some degree by 3D MHD simulations and things that are actually turbulent. And so at least on the 3D MHD side for binaries, I'm not sure, and maybe Julian or Scott can correct me, but I don't know if anybody's characterized the turbulent component from the CBD in a binary system. And I just wanted to mention that damped random walk is maybe good for a flat disk, but if you have a magnetically dominated disk, like a MAD disk, or if you have a warped disk, I don't think that it's clear it should apply at all.
Yeah, great point, thank you. I think, can we just, yeah, thank you.
Yeah, this is Luke Kelly, just a brief addition that I think the excess of these binary candidates is kind of additional evidence that the damped random walk is not a sufficient model and that there could be an excess of periodicity there. And I think that's consistent with some of the Kepler AGN characterizations that have really, really high cadence.
And just to add to that quickly, because it's directly in response to that, I think Alberto.
You made a mistake, Alberto. You walked too close
and some other authors actually looked at the CRTS sample and then had tried to figure out what the number density of sources would be, and then what the amplitude of the gravitational wave background would be, and it was not quite in tension with observations, but close. So there's a lot of ways of folding in these different binary populations together and then confronting them with experimental data that we're getting from Nanograv and now the other PTAs.
Good. Can we bring Sebastian in from the Zoom call? Sebastian, are you ready for us?
Oh yeah, I wanted to make a very similar point that was already made. Yeah, that it really depends on the characterization of the turbulence in binary system of what type of power spectrum we'd expect. But I also just want to make the point that yes, regarding kind of damped random walk or not damped random walk, I think what we should rather look at is a power law in the kind of power spectrum characterization, because any time of power law, if it's -2, -1.5, or minus, 2.5, will always give us kind of this red noise-ish leak, and will always cause us some problems in analyzing our variability data and interpret it as a binary or not binary.
Thank you. Yeah, Zoltan.
We're just going to ask the stellar people whether similar red noise has been understood on stellar binary accretion.
You're going first.
Okay.
Say your name.
Hi, I'm Megan Newsom. Okay, can you go back to the TDE slide? Out of personal preference. Okay, we've talked a lot about red noise, and I saw that it's listed as one of the false signals. And right next to that, I also saw TDEs were listed. And as a very young researcher studying TDEs, I have a selfish personal question of what indeed can I do with my TDE research to help you all here? So I'm curious about that part. Yeah, please, can we go for it? Tell us a little about.
Hello. So this is a topic of tidal disruption of star by supermassive black hole binary. And as you can see here, well, first of all, I performed the test particle simulation. The parameters are 26 solar masses and solar type star. And main point is semi-major axis is 100 Schwarzschild radius. It means much smaller scales than subparsec binary. And then that scale is a merging process due to the gravitational wave emission. And mass ratio is, we adopted mass ratio 0.1. And then question is how star approach to the binary black hole. So we assumed star should be born the massive circumbinary disk around the supermassive black hole binary and caused by self-gravitating instability. And then star accretes onto the 2 points like gas flow onto the mini disk. And then stars enter into the Loschlov radius of either L1 or L3. And then star moved around chaotic motion. And finally, the one star enter into the tidal disruption radius, and the entire star was disrupted. And this is the overview of the tidal disruption of a star by supermassive black hole. And the interesting thing is because the semi-major axis is 100 Schwarzschild radius, it means velocity of orbital velocity is several percent of speed of light. So it means emission from the disk should be taken, should take special relativistic Doppler boosting. So could you show me? Yeah. So here, vertical axis shows bolometric luminosity, normalized bolometric luminosity, and horizontal line shows the time in unit of orbital period, and so blue line shows light curve of secondary black hole case. And
for discussion's sake, could you perhaps wrap up a little bit quickly?
No, quickly. Sorry.
There's some other people
sorry.
waiting.
Yeah.
Thank you.
Yeah, and then as you can see, the luminosity take a special relativistic Doppler boosting, so that's why periodicity is more enhanced. And also secondary luminosity is much larger because the relative angular momentum is very small because of relatively small mass ratio. That's all. Thank you.
Yeah, thanks. So I think in answer to the original question too, you're seeing a little bit of our bias actually. So Chengcheng and I wrote TDEs down as a potential confusing signal in periodic light curves. And we were not imagining like a binary black hole around which a star was disrupted. And then Kimmy brought his slides and put them in and we were like, oh, and then there's that. So can be kind of both something that is tracing a singular system or something that might be an amazing tracer for a double system. So yeah.
Follow up. So for flares like this, how confident are we to distinguish it from, for example, the flare in Spiky? It might be a really simple question.
Could you tell me again your question?
Yeah, so for spiky, there's a flare from self-lensing. I was wondering how flares, maybe features from other mechanisms like a TDE distinguish. Yeah, I guess looking at this, they don't look that similar, but it could be potential confusion. It's just something I don't understand.
Do you have something to share? Great. Is it on this topic or a different topic? Otherwise, we just keep jumping. Go, Marcus.
Okay. Marcus DuPont from New York University. So I've always been curious, what sorts of observational constraints and sort of sanity checks do observers use to make clear distinctions? Because I imagine these sorts of systems to be at very high redshifts and hard to resolve. So what do they use to, set clear markers that this is not, for example, an intermediate black hole binary or stellar mass black hole binary, supermassive black hole binary?
I guess I'm not totally sure I understood the question. Were you thinking of a particular regime in which we might be able to distinguish between, like a particular type of observation that might allow us to distinguish between those different classes?
Yeah. What sorts of signatures differ by black hole binary systems?
I don't know who wants to take a stab at that. So certainly the frequency, if you're thinking about a gravitational wave signature, the frequency regime that you'll be dealing with is going to be super different for the different masses. I know that MREs, which are these extreme mass ratio in spirals, are something that's like potentially going to be very cool with LISA, where you have something that's more like, somebody correct me if I'm wrong, but like an intermediate mass black hole and a supermassive black hole. And then the accretion signatures for the different, and also the environments for different types of black holes. So the supermassive black holes we typically see in the centers of galaxies. And others, we search for intermediate mass black holes all over the place with varying success at actually finding them. So I guess it depends a little on which type of observation you're thinking about. From the perspective of the binaries, I think if you've got some sort of Orville frequency, especially the gravitational wave frequencies are really, really constraining on what the total mass of the system is, and then you can kind of infer what the constituent masses are. I don't know if that's getting at your question, Marcus, but there's a lot of different diagnostics you can try to use to parse that out.
Okay, so I think we're going to Ben.
Go, Ben, go.
Hey, yeah, call back to the question about red noise in stellar binaries. I think all of the main big results that have been published are so obvious just by eye that no one's had to kind of dig through the dirt of digging a periodic accretion signal out of kind of the stochastic accretion noise that's common to these stars. But I think that's something that I think we're at the stage where we've kind of run out of the really slam dunk objects and need to do that more carefully. So I'd be interested in kind of having that discussion further and kind of, comparing notes between these two communities. But to be honest, it's not something that we've had to worry about. So.
Also, Ben, I don't know if it's helpful, but I do have your T-Tori slides at the end of this slide deck. I didn't put them in the front part here because they weren't supermassive black holes, but if there's anything illustrative there, just holler and we'll pull them. They're in the same slide deck. Happy to pull them out, Caitlin.
Okay, sure. Yeah, if the conversation goes there, happy to contribute.
This is Caitlin, just a quick follow-up to what Ben said. There's also, there's been a lot of work on not understood variability in young stars. So following Kepler and MOST, there was a lot of, really nice compilation of all sorts of different phenomena, but it was really much more well characterized as these are the stars with, big dips. These are the stars with big emission features or, brightening features that they're still not well understood, but it hasn't been just an analysis that looked like just noise for the accretion signatures.
Interesting, yeah.
Barry?
Yeah. Hi, Barry McCronin. Can you go back to the original list of ways of detecting binaries? Yeah, I would just add to the methods that we use, the possibility of wobbles and ripples and other things in the broad iron K-alpha line. That's something that we think comes from sort of pretty close into these beasts. And so depending on the relative dynamics in the system, there are wobbles and ripples and other kinds of things that can show up, sort of analogous to Rossiter-McLaughlin effects that people may be familiar with.
I'm making myself a list. I know you guys can't actually see this because I've been sitting in the back of the room, but this will be just for me to update my slides later to include these suggestions.
Talk to me if you want to discuss it more.
Thank you. Yeah, I'll add to this and we'll post them. Yeah, Kimmy, go for it.
Okay, let me quick answer for Chengcheng's question. The main difference between usual circumbinary accretion and TDE case is the magnitude of luminosity. Because usually TDE's accretion rate of TDE is much higher than higher than Eddington accretion rate. So yeah. On the other hand, the usual CV accretion case is sub-Eddington. So this is one of the main differences.
Do you have? Nope.
And would it last as long? So if I have Doppler boost emission that's fed from a circumbinary disk, maybe ideally you would imagine it would last as long as the disk, but how long does this Doppler boost in a disruption last for?
Sorry, I couldn't catch you on your words.
Here, I will. Caitlin doesn't have to write back and forth, but just maybe repeat it.
Yeah, so how long would this Doppler boost emission last in the title? How long until the star is accreted and the signature goes away in these?
You mean the time scale?
Yeah.
Of the right part is, that's a good question. Yeah, the time scale is almost correspond to the obj order of binary period. Yeah, several times binary period.
Okay, we have 5 minutes to wrap up.
Can we take Sebastian, or do we have other more questions? People who haven't asked yet. We've been trying very hard to preference people who either haven't had their voices heard or are more junior. Go for it.
So I wanted to ask something more from the stellar community and not even stars with circumbinary. This is boring stars going around each other. So radial velocity variations are very important in there. We've seen a bit of that. So I was curious because, for instance, we have Wolf-Rayet stars that are extremely variable. And I was wondering if there are some parallels between the problems we have in characterizing binarity in those systems and the prospect of observing double line systems, for instance, for spiky, for instance.
Yeah, Luke Kelly again. I can answer that a little bit. So the parameter space available for using emission lines as diagnostics for binarity is actually extremely limited. So this comes back to, I think what Julian was saying earlier, that, often kind of by definition, as you're getting into the binary regime, you're also moving into the regime where these lines no longer probe the binary motion very effectively, but there could still be some range of situations where it's a useful probe. But I think one other similarity to Wolf-Rayet systems is that one of the limiting factors here is the intrinsic variability of lines in AGN. So again, I think it requires much better characterization of individual AGN variability in their lines to then be able to try to disentangle binary signatures better.
So if I could, I would like to make 2 points based on the slides that you flashed up. So one of them is about potential gravitational wave sources.
Do you want me to navigate?
Yeah.
To the one you sent?
Yeah, the one I sent, and then the one that Steve sent.
What about Sebastian was gonna, I think, respond?
Oh, sorry.
Yeah, sure.
Sebastian, go ahead, I think.
Oh, okay. I just want to make that point. You don't need to show the slide, but regarding kind of how to detect or how to find supermassive black hole binaries in the future, This is what's probably not well known in the community yet, but we are planning this upgrade of the infrared interferometer gravity to gravity plus the VLTI. We're reaching sensitivities of down to K magnitudes 19 then. And with that, we are actually in reach of kind of really testing quite a large number of AGN out to maybe redshift or candidates out to redshift 0.2, 0.3 in quite detail, so that we could probe the structure both of the circumbinary disk, if there is one, and even kinematics of the lines. And what RHD simulations showed that with gravity, we are able to specifically identify these binaries by the lack of the normal sublimation radius that they would have as compared to normal AGN. So we can pick them out from the normal AGN population by their radii, and their sizes in the K-band emission being 10 times larger than this narrow relation that we know. And there's also, well, some people also say we could use the kind of because we spectrally resolve the emission lines, we can also use that to kind of do kinematic and spatial resolution. But of course, again, the problem here is, as some have already said, kinematics in the gas around AGN are quite complicated, and you can mimic, even if you spatially resolve, you can mimic the signals in one AGN that you would expect from two.
So that's really interesting and totally feeds into the detection strategies that I was going to discuss with pulsar timing arrays. So this is the paper that Chengcheng led that we published last year. And we went through the CRTS sources and found some really interesting candidates that we marked up here. So 3C66B is a radio core. That's not one of the CRTS sources, but one like HS1630 is a really prime candidate for gravitational wave detection if it really is a binary. And that's for two reasons. One, it's in a favorable part of the sky that has lots of millisecond pulsars. Two, it's actually really well aligned with a well-timed pulsar, and that can give you up to a factor of 4 extra in detection. So once we know where we're looking for these supermassive black hole binary host galaxies, we can activate detection strategies and actively try to go after the binaries. So we can use Fermi-lat unassociated sources to look for some millisecond pulsars that are in the direction to the source. We can also increase the cadence of timing of the pulsars towards that source. So any kind of high cadence timing campaign, and right now Nanograv has a few of them, would also help detect an individual supermassive black hole binary there. But importantly, Steve sent in a slide which highlights work from Caitlin Witt that she did for Nanograv. This is the next one, I think. Yes, exactly. So having an electromagnetic counterpart is really important, because when you know where to look on the sky, you can improve your upper limits by a factor of 2. And if you have any idea of what the frequency is, you can increase your limits by an order of magnitude. So even if your guessed period is totally off for whatever reason, you're still going to do an order of magnitude better by having that initial guess. So I think that those are two things that are really important right now in terms of gravitational wave searches that I really wanted to make sure that we said. Steve, do you want to go over Chengcheng's results with Sarah?
Sure. Yeah, this is sort of an extension of the work on the left-hand side, but across a more expansive set of injections. So Caitlin showed that yes, it helps a lot to have sky location and to help have some constraints on the frequency. What Chengcheng Liu and Sarah Vigeland did was to really test this and see how having sky location and some sort of redshift constraints and frequency constraints systematically improve your ability to detect or invalidate a binary candidate. So this is kind of on the road to multi-messenger detections of individual sources, and we'll definitely talk about that next.
Yep. So we are now out of time.
I'm going to make my last pitch,
yes,
and that is just
yes.
that the NGEHT is also going to do really awesome stuff, and hopefully identifying samples and maybe actually getting down to really being able to look at some of the binaries in pretty hairy detail, including jet launching and stuff. So I think the combination of things like gravity, and we have, I don't know if Stefan Kraus is actually here with us, but he also is an expert in gravity. So if people are really excited about learning more about this from Sebastian or from Stefan, And then the ENGHT, please come and talk to me. So I think there's a lot of really exciting prospects for kind of trying to tackle this observationally, and really the complementarity between gravitational wave searches and EM searches is really exciting for the future. All right, thank you for moderating us. Thank you all for discussing with us. And I think we get a minute or two.